Hello my dear students, today I would like to discuss Chapter 1 and its exercises of Class 10 Cbse. In this chapter, we mainly discuss Euclid's division algorithm and the fundamental theorem of arithmetic. The first section of this chapter deals with Euclid's division algorithm. Before moving to the division algorithm, we have to see Euclid's division lemma. A lemma is a proven statement used to prove another statement. Here, Euclid's division lemma is used to prove Euclid's division algorithm. The concept of division lemma is very simple. Euclid's division lemma says that any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r with this remainder is always less than b. That is, a positive integer a can be divided by b in such a way that it leaves a remainder r which is less than b. Or we can say, for each pair of positive integers a and b, there exist integers q and r satisfying the relation a equal to bq plus r, 0 less than or equal to r less than b. Remainder is always less than b. Q and r can be 0 also. Also, q and r are unique. That is, q and r are the only integers satisfying this condition. Here, q is called a quotient and r is called the remainder. For example, we can see, take a equal to 7, b equal to 2. We can write 7 is equal to 2 into 3 plus 1. Here, remainder is 1 less than 2. And quotient is 3. Theorem, Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying a equal to bq plus r, 0 less than or equal to r less than b. We can see examples. Take a equal to 7, b equal to 2. We can write 7 is equal to 2 into 3 plus 1. Or take a equal to 17, b equal to 6. Then it becomes 17 is equal to 6 into 2 plus 5. Here remainder r is 5 and quotient is 2. R is less than 6. Next, a equal to 5, b equal to 12. Here a is greater than b. So we can write 5 is equal to 12 into 0 plus 5. Here the quotient is 0 because 5 is greater than 12. The divisor is greater than the dividend. Next one, take a equal to 20, b equal to 4. We can write 20 is equal to 4 into 5 plus 0. Here the remainder is 0. For more examples, take a equal to 10, b equal to 3. We can write 10 is equal to 3 into 3 plus 1. Take a equal to 4, b equal to 19. Here a is less than b. So 4 is equal to 19 into 0 plus 4. Next, take a equal to 81, b equal to 3. We can write 81 is equal to, we can just divide 81 by 3. Here 2, 6, 21, 7. This is divisible by, remainder is 0, divisible by 3. 3 into 27 plus 0. I hope the lemma is clear. Then we can go to division algorithm. Algorithm is a series of steps which gives a procedure for solving a type of problem. Euclid's division algorithm is a technique to compute highest common factor of two positive integers. As you know, highest common factor of two positive integers a and b is the largest positive integer at b that divides both a and b. For example, we can say HCF of 42 and 35. We can see 42 factors are 1, 2, 3, 6, 7, 14, 21, 42. Factors of 35 are 1, 5, 7, 35. Here the common factors are 1, 7 and the largest common factor is 7. Therefore, HCF of 42 and 35 is 7. For large numbers, it will be tough to find highest common factor using this method. So, division algorithm says an easy method to find the highest common factor. Euclid's division algorithm. To obtain the highest common factor HCF of two positive integers say c and d with the c greater than d, follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So we find whole numbers q and r such that c equal to dq plus r, 0 less than or equal to r less than d. Step 2. If r equal to 0, d is the HCF of c and d. If r not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be required HCF. That is, to find the HCF of two positive integers c and d with the c greater than d, first step we have to apply Euclid's lemma to c and d. Then we will get a quotient and a remainder. If the remainder is 0, then the divisor d will be the HCF. If the remainder is a non-zero, apply Euclid's lemma to d and r. Continue the process till the remainder is 0. When we get the remainder r is equal to 0, that stage will be the HCF. This algorithm works because HCF of c and d is equal to HCF of d and r. You can see it in detail through an example. Example, find HCF of 455 and 42. Here 455 is greater than 42. Therefore, we can divide 455 by 42 to get a quotient and a remainder. See, 455 by 42 is, we get 455 is equal to 42 into 10 plus the remainder is 35. Here, since the remainder is a non-zero, we can apply Euclid's lemma to 42 and 35. Then we get 42 is equal to 35 into 1 plus 7. Again the remainder is non-zero, so again apply Euclid's division lemma. Then we get 35 is equal to 7 into 5 plus 0. Here the remainder is 0. Therefore, by division algorithm, we get HCF of 455 and 42 is the dividend at this stage, that is 7. Therefore, HCF of 455 and 42 is equal to 7. Also, we can see that HCF of 35 and 7 is also 7. Also, HCF of 42 and 35 is also equal to 7. HCF of 35, 7 is equal to HCF of 42, 35 is all equal to 7. Next example, find HCF of 4052 and 12576. Here 12576 is greater than 4052. Applying division lemma to this number, we get 12576 is equal to 4052 into 3. 4052 into 3 is 121576. So to see the remainder, here the remainder is 420. Remainder is non-zero, so again apply division lemma. Then we get 4052 is equal to 420 into 9. 420 into 9 is 3780. Therefore, the remainder is 4052 minus 3780. 9 plus 272. Remainder is non-zero. Again apply division algorithm. We get 420 is equal to 272 into 1 plus, here the remainder is 148. Then we get 272 is equal to 148 into 1 plus 124. Here we get 148 is equal to 124 into 1 plus 24. Again remainder non-zero. We get 124 is equal to 24 into 5 plus 4. Again remainder non-zero. We get 24 is equal to 4 into 6 plus 0. We get the remainder is equal to 0. Therefore, HCF of 12576 and 4052 is equal to 4. Also, we can note that HCF of 24 and 4 is equal to 4. Similarly, HCF of 124, 24, HCF of 148 is equal to 148, 124, HCF of 272, 148, HCF of 422, 272, and HCF of 4052 and 420 are all equal to 4. Next example, show that every positive even integer is of the form 2q and that every odd integer is of the form 2q plus 1, where q is some integer. We have to show every odd integer is of the form 2q plus 1 and even integer is of the form 2q. We know that any positive integer can be either odd or even. We can take any arbitrary positive integer. Let a be any positive integer and b is equal to 2. Then we can apply Euclid's lemma to a and b. By Euclid's lemma, we get a is equal to 2q plus r with 0 less than or equal to r less than 2. That is, r can take values 0 and 1. When r equal to 0, we get a is equal to 2q. Clearly, this is divisible by 2. Therefore, a is an even integer when r equal to 0. And when r equal to 1, we get a is equal to 2q plus 1. We know that any positive integer is either even or odd. Therefore, a equal to 2q plus 1 is an odd integer, since a is divisible by 2. And here, since any positive integer is either even or odd, therefore we can say any positive odd integer is of the form 2q plus 1 and any positive even integer is of the form 2q. Next question, show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Here we can take, let a be any positive integer and b is equal to 4. Then by Euclid's lemma, we get a is equal to 4q plus r with 0 less than or equal to r less than 4. That is, r can take values 0, 1, 2 and 3. Clearly, when r is equal to 0, we get a is equal to 4q, and r is equal to 2, we get a equal to 4q plus 2, which is 2 into 2q plus 1. Here 4q is divisible by 2 and 2 into 2q plus 1 is again divisible by 2. Therefore, when r equal to 0 and r equal to 2, a is an even integer. Since any positive integer is either even or odd, we get when r equal to 1 and r equal to 2, r equal to 3, a is a odd integer. A equal to 4q plus 1 and a equal to 4q plus 3. Not divisible by 2. Therefore, this is not even, hence it's a odd integer. These are solved exercises in your textbook, so I am not writing the proper notes. For the exercises that is not solved, I will write the notes. Next example, a sweet seller has 420 kaju burfis and 130 badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? We have two types of burfis, kaju burfis and badam burfis. We have to stack it in a tray so that each stack has the same number and consume the least area of the tray. That is, we have to stack the maximum number possible. To take the same number from each kind of burfis, we have to see what is the common factor, and to consume the least area or to stack the maximum number, we have to find the highest common factor. We can see HCF of 420 and 130 by Euclid's lemma. 420 is equal to 130 into 3 plus 30. Remainder non-zero, then 130 is equal to 30 into 4 plus remainder is 10. And 30 is equal to 10 into 3 plus 0. Therefore, we get HCF of 420 and 130 is equal to Hence the answer is 10. Therefore, the sweet seller can make stack of 10 for both kinds of burfis in each tray. Now we can go to the exercises. Exercise 1.1. First question, use Euclid's division algorithm to find the HCF of first one 135 and 225, second one 196 and 38,220, and third one 867 and 255. First one, to find the HCF of 135 and 225, here 225 is greater than 135. So we can apply Euclid's lemma by taking A equal to 225 and B equal to 135. Since 225 greater than 135, take A equal to 225, B equal to 135 in division lemma. Then we get 225 is equal to 135 into 1. 225, remainder is 225 minus 135 is, here the remainder is non-zero, then apply Euclid's lemma to 135 and 90. Since remainder 90 not equal to 0, apply lemma to 135 and 90. Then we get 135 is equal to 90 into 1 plus here the remainder is 45. Again, the remainder is non-zero. Therefore, we can apply Euclid's lemma to 90 and 45. Then we get 90 is equal to 45 into 2 plus 0. Here the remainder is 0. Therefore, we can stop the procedure. Then we get HCF is equal to 45. Here remainder is 0. We can stop the procedure and HCF is the divisor at this stage. That is HCF of 135 to 25 is equal to 45. Next question, 196 and 38220. Since 38220 is greater than 196, apply division lemma taking A equal to 38220 and B equal to 196. By division lemma, we get 38220 is equal to 196 into 195 plus 0. Here the remainder is 0. Therefore, by Euclid's lemma, we get of 38220, 196 is equal to 196 itself. 190. Next question, 867 and 255. Here 867 is greater than 255. Therefore, apply Euclid's lemma taking A equal to 867 and B equal to 255. Applying lemma, we get 867 is equal to 255 into 3 plus 102. Remainder is 102 not equal to 0. Therefore, apply lemma to 255 and 102. Then we get 255 is equal to 102 into 2 plus 55. Remainder 51. Again non-zero. Therefore, 102 is equal to 51 into 2 plus 0. We get the remainder 0. Then we can stop the procedure and the HCF will be the divisor here. That is, here the divisor is 51. Next exercise, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Here we can take A is equal to any positive integer and B equal to 6. Applying division lemma, we get A is equal to 6q plus r with r is equal to 0, 1, 2, 3, 4, 5 less than 6. R is less than B. When r is equal to 0, we get A equal to 6q. Can be written as 2 into 3q, which is even. When r equal to 2, A equal to 6q plus 2, which is equal to 2 into 3q plus 1, which is divisible by 2, again even. And when r is equal to 4, A equal to 6q plus 4, which is equal to 2 into 3q plus 2, which is again divisible by 2, therefore it is even. When r equal to 1, we get A is equal to 6q plus 1, which is equal to 2 into 3q plus 1. Sum 2k plus 1 form, that is odd, not divisible by 2. When r is equal to 3, A is equal to 6q plus 3 is equal to 2 into 3q plus 2 plus 1, which is equal to 2 into 3 cube plus 1 plus 1. Again, not divisible by 2, therefore this is odd. R equal to 5, A equal to 6 cube plus 5 is equal to 2 into 3 cube plus 4 plus 1. 2 into 2 plus 1 is equal to 2 into 3 cube plus 2 plus 1, which is not divisible by 2. This is because we know 2 divisible by 2, 4 divisible by 2. 2 plus 1 is equal to 3, cannot be divisible by 2. 4 plus 1, not divisible by 2. That is, 1 adding to a even integer cannot be divisible by 2 or cannot be an even integer. We can write this in detail. Let a be any positive integer and b equal to 6. By lemma, we get a is equal to 6q plus r, 0 less than or equal to r less than 6. That is, r equal to 0, 1, 2, 3, 4, 5. That is, a can be 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 or 6q plus 5. Now we can see 6q is equal to 2 into 3q. 6q plus 2 is equal to 2 into 3q plus 1. 6q plus 4 equal to 2 into 3q plus 2, which is all divisible by 2. Therefore, they are even numbers. Then, now we can see 6q plus 1 is equal to 2 into 3q plus 1 equal to some 2q1 plus 1 form, which is not even. Now, 6q plus 3 is equal to 2 into 3q plus 2 plus 1, which is 2 into 3q plus 1 plus 1, some 2q2 plus 1 form, again not divisible by 2. Now 6q plus 5 is equal to 2 into 3q plus 4 plus 1 is equal to 2 into 3q plus 2 plus 1 is equal to some 2q3 plus 1 form, again not divisible by 2. Therefore, they are odd numbers which are odd. Therefore, any odd integer can be expressed in the form 6q plus 1, 6q plus 3 or 6q plus 5. Next question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? To get the maximum number of columns in such a way that the two groups are to be marched in same number, it's enough to find the HCF of 616 and 32. We can find it by Euclid's lemma. We can write it in detail. To get the maximum number of columns in which they can march, it's enough to find HCF of 616 and 32. Applying Euclid's lemma, here 616 is greater than 32. 616 is equal to 32 into 19 plus 8. The remainder is 8. Then again apply Euclid's lemma to 32 and 8. Then we get 32 equal to 8 into 4 plus 0. The stage remainder is 0. Therefore, the HCF is the divisor 8. Therefore, they can march in 8 columns each. Here the HCF is 8. Therefore, they can march in 8 columns each. Next question. Use Euclid's lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Here we have to take any integer and b equal to 3. Then we have to check a square. We have to find the square. A square is of the form 3m or 3m plus 1. I can see. Let a be any positive integer and b equal to 3. By Euclid's lemma, we can write a equal to 3q plus r, 0 less than or equal to r less than 3, where r equal to 0, 1, 2. That is a equal to 3q, 3q plus 1 or 3q plus 2. Then take a equal to 3q. Squaring, we get a square is equal to 3q the whole square is equal to 9q square is equal to 3 into 3q square, which is equal to some 3 into m1 plus 4. Then take a equal to 3q plus 1. Squaring, we get a square is equal to 3q plus 1 the whole square, which is equal to 9q square plus 6q plus 1, which is equal to 3 into 3q square plus 2q plus 1, which is of the form some 3m2 plus 1 form. Next, take a equal to 3q plus 2. Squaring, we get a square is equal to 3q plus 2 the whole square is equal to 9q square plus 4 into 3q plus 4, which is equal to 3 into 3q square plus 4q plus 1 plus 1. This is 3 plus 1. That is some 3m2 plus 1. Therefore, square of any positive integer is of the form 3m or 3m plus 1. When r equal to 0, we get 3m form. When r equal to 1 and 2, we get 3m plus 1 form. Therefore, square of any positive integer is of the form 3m or 3m plus 1. When r equal to 0, we get 3m form. When r equal to 1 and 2, we get 3m plus 1 form. Therefore, square of any positive integer is of the form 3m or 3m plus 1. Next question. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Here we can take a is any positive integer and b equal to 3. We have to find the cube. Let a be any positive integer and b equal to 3. By lemma we get a is equal to 3q plus r with 0 less than or equal to r less than 3. That is r equal to 0, 1 or 2. When a equal to 3q, that is a equal to 3q, 3q plus 1 or 3q plus 2. Then when we have to find the cube of positive integer. So when a equal to 3q, we get a cube is equal to 3q, the whole cube is equal to 27 q cube. That is 9 into 3q cube, which is of the form some 9m1. When a equal to 3q plus 1, we get a cube equal to 3q plus 1 the whole cube, which is equal to 3 cube is 27, 9 into 3. We have to check the form 9m, 9m plus 1 or 9m plus 8. That's why I am writing like this. 9 into 3q cube plus a plus b the whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Applying, we get equal to 9 into 3 q cube plus 3 into 9 q square plus 9 into q plus 1 is equal to 9 into 3 cube plus 3q square plus q plus 1, which is of the form sum 9m2 plus 1. When a equal to 3q plus 2, a cube is equal to 3q plus 2 the whole cube, which is equal to 9 into 3q cube plus 3 square is 9q square into 2 plus 3 into 3q into 2 square is 4 plus 2 cube is equal to 8, which is 9 into 3 cube plus 2q square plus 4q plus 8. That is plus 8 form. Therefore, cube of any positive integer can be written in the form 9m or 9m plus 1 or 9m plus 8.